In the last class, we had discussed that waves are oscillations or some type of disturbances that will carry energy from one point to another point depending upon following parameters. That is, causing that it is a disturbance caused from the source and it will transfer energy from this point to this point depending upon following parameters. That is, variations in pressure or variations in temperature or variations in density. That means this disturbance will travel from here to here if there is a change in pressure or difference in pressure or difference in temperature or difference in density. Then energy will be transferred from this point to this point. That is actually called wave. Now, in this class, we are going to express the wave in mathematical terms. Why? Because whenever we are analyzing any entity on paper, it is always required to be expressed in mathematical notations. Then analysis will be very, very easy. So, for that purpose, we are going to analyze it in mathematically, how wave can be represented in mathematical. For that purpose, I am assuming that I am creating a disturbance that will create a wave that is of transverse in nature. Transverse in nature means, see, this is the disturbance, source of the disturbance, and I am creating disturbance. It is creating a source, maybe sinusoidal variation source with a frequency f. Then it will move from here to here in its direction, maybe wave. While it is moving from here to here, this will vibrate the particles of medium in a direction perpendicular to direction of the wave. I mean to say, I am assuming that if wave is progressing in this direction, then particles of the medium will be vibrating perpendicular to the wave direction, and the frequency of this particle will be equal to the frequency of the source. Whenever wave is progressing from one point to another point, it will disturb all the particles and they will oscillate from their mean position with a frequency of f. Assuming that source is vibrating at f and it will also vibrating the particles of the medium with a frequency f. That means to say, initially the particle, this particular particle is at mean position and it is going to maximum or extreme position. In terms of displacement, I may take it as maximum displacement of A, and coming back to mean position, and after coming to mean position, it is going back to another extreme position and coming back to original position. For this entire cycle, it is taking a time of t, and I can assume that from here to here it is taking 3/4 period. From here to here it is taking another t/4. From here to here it is taking 3/4. And then from here to here t/4. Total time period is t. For one particle it is taking, and for one oscillation it is taking a time of capital T. And after time t, the particle is in the same position when it is at t equal to 0. So it is vibrating or doing simple harmonic motion with a period of t and maximum amplitude or maximum displacement of A. Then I can replace, I can represent this particle displacement with mathematical equation of y of t equal to maximum displacement is A, and I am taking sinusoidal function in order to represent the periods, and I can assume that it is going at a frequency or angular frequency of omega. How we can represent omega? It will be how much time it is taking to oscillate. Here if you observe, particle is starting from t equal to 0 and it is taking a time of capital T to get the original position or to get back the original position. I mean to say, in order to undergo a phase difference of 2 pi, it is taking a time of capital T. In other terms, I can take it requires t seconds to undergo a phase difference of 2 pi. For unit time, it is doing a phase difference of 2 pi by t, and we can call it as a angular velocity omega. So finally, my equation for the displacement of particle will be like y of t equal to a sin 2 pi by t into t. And I am repeating, this is the displacement equation of a particle, single particle, not wave. And we are further moving from displacement of a particle to wave of a mathematical expression of a wave, and we are going towards that. So what is the displacement of the particle? The equation of the displacement of the particle, y of t equal to a sin of omega t, and omega is 2 pi by capital T. Here T is the time period of the particle to undergo one oscillation. That means if this is the particle and here I am creating disturbance, the particle of medium doing one oscillation from here to here and here to here, here to here, finally it is taking a time of t. For consideration, just assume that at any random time, maybe at t equal to t naught, what is the displacement of the particular particle? I can say y equal to y of t minus t naught is equal to a sin of 2 pi by t into t minus t naught, or y of t minus t naught is equal to a sin of omega into t minus t naught. But at time randomly at t equal to t naught, or I have taken disturbance started t equal to 0. After a time of t naught, this disturbance also do some displacement, or this disturbance will go a distance from its source. I am assuming that the distance is x. Then how I can write x equal to v into t naught, where v is velocity of wave. Velocity of wave means if v is the velocity of wave and in a time t naught, the displacement or disturbance or this wave can progress from 0 distance to x distance. So this is the distance traveled by the wave x, that can be expressed as v into t naught. From this expression I can write t naught equal to x by v. So just substitute that one into the previous equation. How I can write y of t minus x by v is equal to a into sin of omega into t minus x by v. So if we reorganize the same equation, so y of t minus x by v is equal to a sin of omega t minus omega by v into x. Assume that, or else a particle is doing one oscillation in a time of t. In the meantime of t, wave also progress a distance. That means whenever a particle is doing one oscillation, meantime disturbance will go to some distance. That means the distance covered by the wave in one unit time, one cycle of time, is actually called wavelength. That means lambda or wavelength is the distance covered by the wave or displacement covered by the wave in one oscillation period of the particle. Then how I can write velocity? Velocity of the wave equal to displacement or distance by time. Or clearly speaking, as I am taking velocity, it will be displacement by time. Here displacement is lambda and time is t. So substitute the same in the above equation. Then y of t minus x by v is equal to a sin of omega t minus omega by lambda whatever to t into x. If I reorganize the same, then y of t minus x by v is equal to a sin of omega t minus omega t by lambda into x. So this is the equation what we have arrived just. And as the variables are only t and x, why? Because velocity won't change in a medium until unless we are changing, if you are changing frequency of the source. So I can take this as a function of time and distance. Then I can write a sine of omega t. Then I can write omega as 2 pi by t into t divided by lambda into x. So finally, y of t comma x equal to a sine of omega t minus 2 pi by lambda into x. Assume 2 pi by lambda equal to k, then y of t comma x is equal to a sine of omega t minus kx. This is called wave equation. So it is a function of both time and space. So one is angular velocity, another one is called actual angular number. This is the equation of the wave. This will be same for transverse wave or even longitudinal wave. Whatever equation will be same. So in this class we have discussed how we can represent wave in mathematical notation. This is the wave equation where t comma x equal to a sin omega t minus k. That's all.